Hello students and welcome to our help video. This is 9-10 and we have a help video discussing this extremely important calculation. We are in Unit 9 right now, stoichiometry, and one of the most important calculations we learn in all of chemistry is called mass to mass, a mass to mass calculation. To do this mass to mass calculation, it helps to have the chart out in front of you, because we are doing stoichiometry and this is the conversion chart. In Unit 8, we learned that if you have a chemical equation that is balanced, that is a very powerful tool. And very often in chemistry, they're going to give you the mass of one thing involved in the chemical reaction and ask for the mass of something else. Either give you a mass of a reactant and ask how much product it could take, or give you the mass of or how much product it could make, or they could give you the mass of a product and ask you how much reactant it would take to make that. But this is one of the most fundamental things. This is stoichiometry, and stoichiometry simply means that you're going to use the proportions that are established in a balanced chemical equation to solve a multitude of problems. Today we're dealing with one of the most important ones, one of the most common calculations of all. We're dealing with mass to mass. Here we go. In this problem, we have acetylene, which is a compound with the formula C2H2, and it is used as a fuel. It is used as a chemical building block, and it is often combusted. If you recall, in a combustion reaction, they will take a hydrocarbon, carbons and hydrogens. They'll burn it in the presence of oxygen to make carbon dioxide and water. Be sure you balance this correctly. This is a great opportunity to use the Hollister rule. The Hollister rule, the acronym for Hollister Clothing Company, is HCO. And it tells us that we want to balance hydrogen first. We have two hydrogens here, so we would think we have two there. So we would think the hydrogens were already balanced, but there's a problem there. If we have two here and two here, that means we would only have a 1 in front. 1 times 2 is 2, but we cannot have an odd number in front. So we take that 1 and double it to a 2. 2 times 2 is 4, so we now have to put a 2 in front of here. 2 times 2 is 4. The hydrogens are balanced. We now move on to carbon, HCO. 2 times 2 carbons is 4, so we put a 4 in front. 4 times 1 is 4. And our last one that we now work with is oxygen. Here we have 4 times 2 oxygens is 8, plus 2 times 1 is 2. 8 and 2 is 10. We put a 5 in front. We now have a balanced equation. And now let's take a look at the problem. What mass of oxygen? They're asking for what mass of oxygen would we need if we were going to burn 34.28 grams of acetylene. So they want to know how much oxygen we would need, a mass of oxygen, to burn a certain amount of acetylene. When we look on this, they're giving us the mass of acetylene, and they're asking for the mass of oxygen. So to do this problem, we're going to have to convert the mass of acetylene to moles of acetylene. Then we're going to use the balanced chemical equation to go moles of acetylene to moles of oxygen. Once we know moles of oxygen, we'll multiply by the mass of oxygen in 1 mole, the molar mass, and that will get us how many grams of oxygen we need. It's a 1, 2, 3-step problem. So when we look down here on the actual problem, we've got step 1, step 2 is our mole to mole, and step 3 we're multiplying by the molar mass of oxygen. We need 3 setups. Looking back over here, our first setup, we want 1 mole of acetylene over its mass from the periodic table. So we need to have a periodic table. We're going to want 1 mole of acetylene on top, and we're going to want the mass from the periodic table on the bottom. Acetylene C2H2, there's 2 carbons at 12 each, is 24O2. There's 2 hydrogens at 1008 each, that's 2016. If you used 1.01 for hydrogen, that's fine. We add those two together, it's 26.036 grams of C2H2 for every 1 mole. Why am I putting the mass of this on the bottom and the mole on top? We look over here, we want mole on top and mass on the bottom. But if we forgot that, it's very easy to realize that we're given grams of C2H2. So grams of C2H2 must be on the bottom so that they cancel out. Grams will cancel with grams. And now we're at moles. So we now have converted to moles. When we look on our chart to go from moles of C2H2 to moles of oxygen, we need the mole-to-mole ratios, the coefficients from the balanced chemical equation. The one we're trying to find is going to be on top. That would be moles of oxygen. The one we're given, moles of C2H2, would be on the bottom. And we get those from the balanced equation. When we look at our equation, it's 2 moles of C2H2 for every 5 moles of oxygen. We can write inequality two ways. We can put 2 moles of C2H2 on top and 5 moles on the bottom, or 5 moles on top, 2 moles on the bottom. Which one of those do we need? We want moles of oxygen on the top. The moles of the one you're trying to find goes on top. We're trying to find oxygen. There's moles of oxygen. 5 moles of oxygen for every 2 moles of acetylene. If you forget to do it that way, we've got moles of C2H2 here. We want that to factor out through dimensional analysis. So moles of C2H2 cancel with moles of C2H2. And we're left now, we are in moles of oxygen. Our third and final step of this problem, we've got to go from moles of oxygen to mass of oxygen. And we're going to need the periodic table. Grams of PTOT from the periodic table. So what is the mass of 1 mole of oxygen? Well, there's 2 oxygens in there at 16 each, that's 32. We're going to put the mass on top, 32 grams. Mass is on top, moles go on the bottom, as it tells us to do right here. Mass on top, moles on the bottom. If we forget to do that, if we know we've got moles of O2 here, it needs to cancel with moles of O2 there. So we take 3428 divided by 26036 equals, times 5 equals, divided by 2 equals, times 32 equals. We would have 105.3 grams of oxygen needed to burn 34.28 grams of acetylene C2H2. We have another mass-to-mass problem to take a look at here. How many grams of carbon dioxide? How many grams of carbon dioxide would be produced during the burning of the 3428? How many grams of carbon dioxide would be produced? So our question is grams of carbon dioxide would be burned by 3428 grams of acetylene. Our given goes right out front. Our first step is going to be just the same. This is another mass-to-mass problem. Mass of acetylene, this time to mass of CO2. So the first step is going to be identical. We've got to go mass to moles. But now we're working with CO2. So we have to go up to the balanced chemical equation, and we will see that it's 4 moles of CO2 produced from every 2 moles of C2H2. 4 to 2. The CO2 goes on top. What we're trying to find goes on top. If I have moles of C2H2 there and moles of C2H2 there, they would cancel. When we look back on the chart, moles of C2H2 to moles of CO2. What we're trying to find is CO2. It needs to be on top. It's 4 to 2. Now we need the molar mass. We need the mass of 1 mole of CO2. There's 2 moles of oxygen in there. 2 times 16 is 32. There's 1 mole of carbon in there. 1 times 1201 is 1201. Add those up. It's 4401 grams. How do I know which one's on top, the mass or the moles from this equality? We can look back here. The mass should be on top. We're going from moles of CO2 to mass. The mass should be on top. It's on top. If we forget that, we see moles of CO2 here, we see moles of CO2 here, they're able to cancel. We would take 3428 divided by 26036 equals times 4 equals divided by 2 equals times 44 equals. You would produce 115.9 grams of CO2. On our next video, we will take a look at how do we solve the problems on the back, number 3 and 4.